All right, let's look at another example of Bayes' rule. We will do again disease testing, but now we will look at this problem from different angles, and we'll try to write it down as a decision tree. So again, the problem is we would like to test whether a person has a disease or not, and we introduce variable d, it equals to 1. It indicates that you have a disease, and let variable t equals to 1 indicate that you have a positive test. And instead of writing the problem in words, we're going to write it as a decision tree. So the patient either has disease or has no disease, and you remember that a prevailing rate of the disease in the population is 2%, so the prior probability is 0.02. And then if person has a disease, person can be tested positive or negative on the test, and the test is 95% accurate, meaning that if person does have a disease, then with 95% probability, the test will say so. And also test has 5% false negatives. In 5% of the cases, a sick person will be identified as healthy. And for a healthy person, we have 1% of false positives and 99% accuracy. All right. So if we now the question is, if we get a positive result, are you really a sick person or not a sick person? How do you interpret these positive results on the test? So another way to write this problem is to use the joint probability table. So we have two values of d and two values of t variable, and the probability that t and d, so it's a probability that person is tested positive and has disease, is, you remember, we can just write it down using conditional. It's probability that person tested positive and have a disease times the probability that person has the disease, right? Well, we know this one, a probability of t given d from the previous slide. So if person is sick, then probability of having a positive test is 0.95. So it's 0.95. And the probability that person has disease is, you remember the prior probability was 0.02 times 0.02. So let's go to R and calculate that. So we have 0.95 times 0.02. So we have 0.19. That's exactly what we have in this table. Okay, 0.19 is the joint probability that person sick and tested positive on the medical exam. So that's how this joint probability can be calculated from conditional probability. Again, we have the rules that allows us to move between conditional and joints. And now if we apply the Bayes rule to this example, and if we'd like to calculate probability that person actually sick, given that the test became positive, so it's, you remember it's just the probability, the joint one of d and t divided by the probability of getting a positive test. Well, this one we know, we calculated this one already, 0.019. Now the probability that the person gets a positive test, so probability of having positive test is just probability of getting positive test when person has disease times the probability that person actually has disease, plus probability of getting positive test when person does not have disease times the probability that the person does not have the disease. So we have those values from the formulation of the problem. If you calculate it out, so the first one, this one we calculated already, 0.019. This one is 0.0098. Then you add them up, and when you divide, you get this 0.66. So if you get a positive test, then the probability is 66% that you actually have a disease. But another way to think about this is just intuitively. So Bayes' rule is nothing but a common sense. We're gonna do the same experiment as we did for the breast cancer. So imagine you have 100,000 people, and assume that 2,000 of those have a disease, right? So that's our 2% prevailing rate. So you start with a relatively large population, and we know on average 2% will have a disease. So in our case, we'll just uh, take 2,000. And we also expect that 1% of the disease-free people to test positive. So so we have 100,000 people, and 2,000 have disease, and the rest of them, which is 198,000, do not have the disease. And out of those, you remember that 1% will be tested positive. So 1% is, so probability that you will get a positive test, let's start. So among people who are actually healthy, which is 198,000, 191, so almost 2,000 people will get a positive test. This is out of the healthy people, and then 95% of the sick people, 95% of the sick people also will get a positive test. So that's the probability of seeing a positive test. So totally we have 2,880 people will be tested positive. Okay, and now out of those people, only 1,900, which is 0.95 times 2,000, is this number, the people who are actually sick. So people who get tested positive and actually sick is 1,900, and total positive tests is 2,880. So if we take a ratio of those two numbers, we actually get this 0.66. So we get the same answer. So again, Bayes' rule is nothing just